Okay, so this is problem 1, and in this problem we place two aluminium blocks. So here's block 1 and here's block 2 next to each other. They both have a mass of 400 grams, which is 0.400 kilograms, and they've got a specific heat of 910 joules per kilogram per Kelvin. Initially, this block here is at 30 degrees C, and this one here is at 90 degrees C. And we're asked in part A, what is the final temperature? Okay, now possibly you can see that because they've got the same mass and they're made of the same substance with the same specific heat, the final temperature is just going to be the average temperature of these two. So it'll be 60 degrees C. Okay, but let's go through and solve that just in case to model how we do a more complicated problem where, say, the masses weren't the same or the specific heats weren't the same. What we know is that the total heat transfer is 0 because we're assuming that no heat flows between the blocks and the environments. So what we can write is M1C1 times the change in temperature of block 1 plus M2C2 times the change in temperature of block 2 is equal to 0. That tells us that no heat is lost to the environment. So we've got M1C1. Now the change in temperature is equal to the final temperature minus the initial temperature of block 1. Now we don't need to put the subscript 1 on the final because they come to the same final temperature. They come to thermal equilibrium. And then we've got plus M2C2 TF minus T initial 2 equals 0. Okay, so what we're trying to do is solve for TF. So on the left-hand side, let's pull TF out as a common factor. We've got M1C1 plus M2C2. And then we'll put the initial temperature terms over to the right-hand side. So we've got M1C1 T initial 1 plus M2C2 T initial 2. And so that tells us that the final temperature is equal to M1C1 T initial 1 plus M2C2 T initial 2 over M1C1 plus M2C2. Okay, so this is our general equation. In this case, we know that M1 equals M2 equals 400 grams, and that C1 equals C2 equals 910 joules per kilogram per Kelvin. Okay, so using this, M1C1 is just MC, as is M2C2. So we can pull MC out the front, and we've got T, sorry about the bad writing, initial 1 plus T initial 2. And then down the bottom, this is MC plus MC, so that's 2MC. These cancel, and so this is just the initial temperature of 1, which was equal to 30 degrees, the initial temperature of 2, which was 90, and then we divide by 2, and so that gives us 60. But like we said at the start, in this case, that's just taking the average of those two temperatures. But this would work even if the masses were different and they were made from different materials. Okay, in part B, it then asks us to calculate the change in entropy of the two-block system. So in order to do this, we can imagine heating block 1 gently up to 60 degrees and cooling block 2 gently down to 60 degrees. And for each of these processes, we can calculate the change in entropy. So the change in entropy of block 1 is going to be the integral from the initial state to the final state of dq over t. Now we need to express dq in terms of T, the temperature. We know that Q, the amount of heat flows, is equal to MC times the change in temperature. So this tells us that to change a little temperature, dt, we need to add a little heat, dq. So this tells us that dq is equal to MC dt. So what we're going to do is put this expression into here. So this is equal to, from the initial to the final, of MC dt on T, and so this is equal to MC times, now we've got the integral from the initial to the final of dt on t. So this will just be log. So we've got mc times log of t final minus log of t initial equals mc log t final on t initial. Now we'll have the same expression for 2, but with block 2 where the initial temperature is 90 degrees and the final temperature is 60 degrees. Okay, so let's evaluate it for block 1. In that case, we've got 0.400, that's the mass C, that's 910, times log, the final temperature is 60 degrees, so that's 60 plus 273 over the initial temperature, which is 30 plus 273. And so solving this on the calculator, we end up with 34.365 joules per Kelvin. And then we need to do it for the second block, which has the same mass, the same specific heat, but now the initial temperature is 90 degrees, so 90 plus 273, and the final temperature is still 60 degrees, so 60 plus 273 still, but the initial temperature is now 90 degrees, so 90 plus 273. We put that into the calculator and we end up with minus 31.3987 joules per Kelvin. And then delta S total, the total change is just the sum of these, delta S1 plus delta S2. And solving that on the calculator, we do this plus this, and we end up with plus 2.97 joules per Kelvin. So we should check that it's positive because we expect this to be positive because entropy increases with time. It is, so that suggests that possibly our answer is correct. Okay, this is problem 2, and in this one we're told that we have 2 moles and O2 gas, it undergoes a free expansion from a volume of 40 litres to a volume of 80 litres. So we can do this on a PV plot. Here's P, here's V. Initially it's at 40 litres. Finally, it's at 80 litres. And then because it's an free expansion, it's not in equilibrium between these two places. So we can't draw a path between those two on our PV plot. But what we're asked to do is calculate the change in entropy. So we know that for an ideal gas, the change in entropy for a reversible process is given by NCV times log of the final temperature over the initial temperature plus NR log times the final volume over the initial volume. Okay, now this is for a reversible process. This is not a reversible process because it's highly unlikely that the molecules will put themselves all back randomly into half of the container. But because entropy is a function of state, it doesn't actually matter what path we take between these 2 points. So we can choose an isotherm, and then if we choose an isotherm, we can apply this equation because the isothermal process is reversible. Okay, so this is an isotherm. These two states, the initial and final state, are at the same temperature. So we've got that the final temperature is equal to the initial temperature. That's always true for a free expansion. And so we've got this is log of 1. And so when log of 1 is 0, so this whole term here is equal to 0. So we've got that our change in entropy is equal to NR times log of the final volume over the initial volume. And these are all things that we know. We know that N is 2 moles. We know that R is 8.314. We know that our final volume is 80 and our initial volume is 40. Those are both in litres, so we don't need to worry about converting it. So we've got 2 times 8.314 times log of 80 divided by 40, which is 2. and we can solve that on the calculator, and we end up with 12 joules per Kelvin. That's to two significant figures. It's 11.5 to 3, but the moles was given to two significant figures, so we should give it to two significant figures. The volume was either 1 or 2, so we'll go with 2. And then it says, is this process reversible? And the answer is no. Free expansion is not reversible, as it is highly unlikely that the molecules will randomly return to half the volume. And we would expect our change in entropy to be positive, which it is, because this is an irreversible process, and through time entropy needs to increase. Okay, so this is problem 3. It's actually a little bit harder than it first appears. So in this one, we're asked to rank these A, B, C, and D in order of the change in entropy. And we know that the change in entropy is equal to Q over T for isothermal processes, which is what all these are. The problem is that Q is a little bit hard to calculate. For isothermal processes, we know that the change in internal energy is equal to 0, and we also know from the first law of thermodynamics that that's equal to Q plus W, the work done on the substance, which is the area under here. And so we have Q is equal to minus W, which is equal to W is equal to the integral of minus P dV. So we can make this the integral of P dV. And now, because these are all isotherms, we've got PV is equal to nRT, where T is constant, and so P is equal to nRT on V, and we can substitute this in here, and we end up with Q is equal to the integral of nRT on V dV, and that's from the initial volume, which they've all got the same initial volume here, to the final volume, and there's two different final volumes. Okay, so doing this, nRT, that's a constant, so we can pull that out the front, and then we've got the integral of V dV on V, and doing this integral, we know that the integral of 1 on the x is log x, so this is equal to nRT log, and we've got V final minus log V initial. And so this is equal to nRT log V final over V initial. Okay, so Q, we can substitute this in. So we've got delta S is equal to nRT log V final on V initial. And then this is over T, and these cancel out. So this is nR log V final over V initial. Okay, now for A and C, they have the largest V final. They've all got the same V initial. So this tells us that for A and C, we've got the same value, and then for V final for B and D is equal to each other but less than this. So the change in entropy is less than A and C but equal to each other. Okay, problem 4. In this problem, we have a Carnot engine whose low temperature reservoir is at 17 degrees C. So that's equal to 17 plus 273 equals 290 kelvins. And it has an efficiency of 40%. So the efficiency is 0.40. And we're asked by how much should the temperature of the high temperature reservoir be increased to increase the efficiency to 50%. So what we want to know is what's the change in temperature of the high temperature reservoir. One way we can approach this is to calculate the initial temperature of the high temperature reservoir, then the final temperature of the high temperature reservoir, and from that we can get the difference. So let's do it that way. We know that the efficiency is equal to 1 minus the temperature of the low temperature over the temperature of the high temperature. Let's rearrange this to get it as a function of TH, because that's what we're trying to calculate. So we have TL over TH is equal to 1 minus the efficiency. Okay, and from this we can see that by switching these two, TH is equal to TL over 1 minus the efficiency. Okay, so currently we've got that TH is equal to TL, which was 290 over 1 minus 0.40. Solving that, we end up with 483.33 kelvins. And TH dash, at the higher temperature where we have the efficiency of, we're told we want 50%, so epsilon dash is equal to 0.50. That's equal to 290 because we're not changing the temperature of the low temperature reservoir over 1 minus 0.50. And that is equal to 725 kelvins. And so the change in temperature of the high temperature reservoir is equal to the final 725 minus 483. And solving that, we end up with 97 kelvins as the change in temperature. Okay, so this is problem 5. We've got this figure here, and we're told that we've got 1 mole of gas and it's undergoing this cycle, and that P up here, so P is equal to 2P naught, and here V is equal to 2V naught, and that P naught equals 1.01 times 10 to the 5 pascals, and that V naught is equal to 0.0225 meters cubed. Okay, and in part A, we're asked to calculate the work done during the cycle. Okay, so that's the work done going from A to B, B to C, C to D, and D to A. Okay, so we know that the work done from A to B is the same as the work done from C to D, and that equals 0 because the volume's not changing. So all we need to do is calculate the work done from B to C. So that's the work done along here. So in this case, it's an expansion, so the work done on the gas is going to be negative, and it's just equal to the area under this rectangle here. So the work done is equal to the pressure times the change in volume. The pressure that acts at is P, which is 2P0. The change in volume, well, the final volume, sorry, we needed the negative because it's an expansion. The final volume is 2V naught, so that's 2V naught minus V naught. And so this is going to be equal to minus 2P naught V naught. We can substitute in our values here, so that's minus 2 times 1.01 times 10 to the 5 times 0.20225. And solving this one, we end up with minus 4,545 joules. We also need to calculate the work going from D to A. So the work from D to A is equal to, in this case, it's a compression, so we should end up with a positive answer, but it's given by minus P times the change in volume still. And so the pressure in this case is equal to P naught. The change in volume, well, the final volume's V naught, the initial volume's 2V naught, and so these negatives will cancel out, and so we'll end up with P naught V naught, which is equal to 1.01 times 10 to the 5 times 0.0225. And so solving this one, we end up with 2,273 joules. Okay, so our work done around cycle, we just need to sum up the work along each path. So that's equal to 2,273 minus 45,045 joules, and that is equal to minus 2,273 joules, which we can write as minus 2.27 kilojoules to three significant figures. Now, if we wanted to save some time, we could have realized that the work done, this part of the rectangle, is positive under AD and negative under BC. So if we wanted to get the work done around a cycle, technically all we had to do was calculate the area inside the cycle. Okay, part B. We're now asked to calculate the energy added as heat during the stroke A to B to C. So we want the heat added as it goes from A to B to C. Okay, so we're going A, B, B, C. So we can calculate the heat added as it goes from A to B, as this is a constant volume process. So in this case, the heat added is going to be equal to NCV delta T. And so we know that CV is F onto R. And so this will be N times F onto R and then delta T. But what we can do for T is use our ideal gas law. PV is equal to nRT, which tells us that T is equal to PV over nR. So our change in temperature is going to be the temperature at B minus the temperature at A. So that'll be PBVB over nR minus PAVA over nR. And you can see these nRs will cancel out. And so F on 2, we were told it was a monotonic gas. So we've got 3 over 2. Now the pressure at B, that's 2P naught. The volume at B is still V naught, and this is minus P naught, V naught. And so this is equal to 3 over 2 P naught, V naught. Okay, so we've found Q from A to B. We also need to find Q from B to C. Now in this case, it's a constant pressure process. So we have N times F plus 2 on 2R, and we've got PC VC on NR minus PB VB on NR. Once again, our NRs nicely cancel, and so we have 5 over 2 in this case because F is 3 times PC VC, so that's 2V naught times 2P naught minus, now the pressure at B, that's 2P naught, but the volume at B is V naught. Okay, so we've got 4 V naught P naught minus 2 P naught V naught. So that will end up as 2 P naught V naught inside the brackets. And so this will be 5 P naught V naught. Okay, so Q total is going to be 5 P naught V naught plus 3 over 2 P naught V naught. So we can write this as 13 over 2 times P naught V naught, which is times 1.01 times 10 to the 5 times V naught, which is 0.0225. And solving that, we end up with 14,771 joules, and so we can write this as 14.8 kilojoules. Okay, part C then asks us for the efficiency of the cycle. Okay, so by definition, the efficiency is what we get out divided by what we pay for. So what we're getting out is the work done by the gas, and that's over QH, the amount of heat that we put in during the intake strokes. Okay, so we've calculated the amount of work. It's up here. This was the work done on the gas. This is the work done by the gas that we're getting out. So because it's got the absolute value sign here, we also need to lose that sign. So this is 2273. The heat entering during this part where it's gaining its heat is equal to 14,771. Okay, so we solve that and we end up with 0.154, which tells us that the efficiency is equal to 15.4%. Okay, part D now asks us what is the efficiency of a Carnot engine operating between the highest temperature and lowest temperature that occurs in the cycle. Okay, so the lowest temperature will be A because it's got the lowest volume and pressure. The highest will be C because it's got the highest pressure and temperature. So we know that the efficiency is equal to 1 minus TL over TH. And so this is 1 minus TL, that's the temperature at A. So just using this temperature again, we've got PA VA over NR over PC VC over NR. Okay, the NR's cancel, and so we've got 1 minus now PA, that's PO VO. And at C, we've got 2 PO and 2 VO, so multiplying those together, we've got 4 PO VO. And so you can see these cancel, and we have 1 minus a quarter, which is equal to 3/4, which is equal to 0.75 or 75%. So that's the Carnot cycle efficiency between these two temperatures. And then part E goes on, is this greater than or less than the efficiency calculated in C? And it is greater than. It has to be greater than because the greatest efficiency is for a Carnot engine. So this is greater than C as expected. The Carnot engine is the most efficient type of engine. Okay, and that's how we solve that problem. Okay, so this is problem 6. In this one, we're considering a building. The inside of the building is at 22 degrees C. The outside of the building is at 25 degrees C. We've got a heat pump, which is a Carnot engine working in reverse, working to cool this building, and its coefficient of performance is equal to 3.8, and so it's effectively moving heat out of the building. It's doing work in order to help move this heat, and that's coming out here. We're depositing this amount of heat outside the building, and we're told that the heat pump delivers 7.54 megajoules as heat from the building, so that's this QH, so each hour. So QH is equal to 7.54 megajoules, and this is over time, and this is per hour. So what we've been asked to find is the rate at which work is done. So what we want is the work over time. What's that equal to? Okay, and we know that the coefficient of performance for a refrigerator is given by what we want, which is QL, over what we pay for, which in this case is the work. Okay, so we know K here. What we want to do is get QL in terms of QH, which is what we know, in order so that we can use this equation. So looking at this figure, we can see that QH, that's the heat pumped out of the building, is equal to the work done plus the heat absorbed from the building. So we can rearrange this because this tells us that QL is equal to QH minus W. We can put this up here. So we've got QH minus W over W, And so this is equal to QH over W minus 1. Okay, now what we're going to try and do is, because it's work that we want to find, we're going to rearrange this to make work the subject of our equation. So we've got QH over W is equal to K plus 1. And so that tells us that work is equal to QH over K plus 1. Now what we're actually trying to find is work over time. So we have that the work over time is equal to, because I've divided this side by time, I need to divide this side by time. So that's QH over time over K plus 1. I put it over the QH because that's what we know. Okay, so now we've got it in terms of things that we actually know. So this is 7.54 megajoules, so that's times 10 to the 6 per hour. And this is, well, divided by the time. So per hour, in an hour, it's 60 times 60 seconds. So that's the time there. And K is equal to 3.8 plus 1. And so solving this on the calculator, we have 436 watts, which is equal to 440 watts to two significant figures. Problem 7. In this problem, initially we have 50 particles, and we're asked initially to calculate the multiplicity of the central configuration. So the central configuration will be when we've got 25 here and 25 here. And in order to do that, we'll need to use our equation W is equal to n factorial over n1 factorial n2 factorial. And so here W is equal to 50 factorial over 25 factorial times 25 factorial. To solve this, we end up with 1.26 times 10 to the 14. You can just solve that one in the calculator. Part B then asks us for the total number of microstates. Okay, so each of the particles that we add can be added to one of two boxes. So each one contributes a doubling to the number of microstates. So because we've got n in this case, the total number of microstates is 2 to the power of n. So in this case, it's 2 to the power of 50. And solving that on the calculator, we get 1.13 times 10 to the 15 states in total. Part C then asks us for the percentage of the time the system spends in the central configuration. So this is the number of ways it can be in the central configuration. This is the total number of states. So the percentage of time it spends in the central configuration is just going to be 1.26 times 10 to the 14 over 1.13 times 10 to the 15. And solving that on the calculator, we end up with 0.111, which is equal to 11.1% of the time in that exact central configuration. Okay, we now have a few more particles. We've got 100 particles, and we're asked to calculate the same things. So in part D, we need to calculate the multiplicity of the central configuration. So in this case, we've got 100 particles in total, and we've got 50 in each state. Okay, so working out this one, we end up with 1.01 times 10 to the 29. If your calculator can't cope with these numbers, you may have to resort to using Excel or use Stirling's equation to try and simplify it a bit initially. Okay, and then E, we're now asked to calculate the total number of states. So that's 2 to the n, which is 2 to the 100 in this case. So this is equal to 1.27 times 10 to the 30. And then the probability of the fraction of the time it spends in this central state is going to be given by 1.01 times 10 to the 29. That's the number of microstates in that central state divided by the total number of states. Solving that, we end up with 0.086 80, which is 8%. So it spends 8% of its time in this central state. And then finally, we're given now 200 particles and we need to do it again. So calculating the multiplicity, this will be 200 factorial over 100 factorial times 100 factorial, which if you solve this on the computer, you end up with 9.25 times 10 to the 58. H, we then ask for the total number of states. That'll be 2 to the 200, which will be equal to 1.61 times 10 to the 60. And then we're asked for what's the probability of finding it in this exact central state. So 9.25 times 10 to the 58 over 1.61 times 10 to the 60. And so this is equal to 5.7%. And then part J asked us about, does the time spent in the central configuration increase or decrease with n? Well, it decreases with n, and that's because there's more configurations that it can spend time in. So if the question was rather how much of the time does it spend in the central half of the configurations, you'd actually find that that increased with time. But in the exact one single central configuration, that decreases with n.